Hello, welcome back. This is Calculus by Dr. Oz. So today we're going to practice what we call absolute or conditional convergence for the given infinite series. But just to remind you, what is an absolute convergence and what is a conditional convergence? So we call an infinite series an to be absolutely convergent when the series, the absolute value of the n term, which is an, is convergent. So instead of showing the convergence of series an, we check the convergence of the absolute value of an. And if that converges, then the original infinite series is absolutely convergent. And we say that a given series is conditionally convergent, okay, when the original series is convergent, but not the infinite series of the absolute value of an. So as you see from the definition, that absolute value of an in the infinite series form may be divergent. So that takes you all the way back to the conditionally convergency. But if the absolute value an in the series form is convergent, then you go back and call the original series to be absolutely convergent. Okay, and we have a test about absolute convergency. So if the series absolute value of an is convergent, then it's forced to have that the infinite series an also converges. That makes the infinite series an absolutely convergent. Okay, so this is a very nice test to apply. And in general, if you have an alternating series, this is one of the ways to get the alternating part of the given series, and then using other tests to show the convergency. And if that is convergent, then the alternating version of the series is also convergent. So we call it like absolutely convergent, in fact. Okay, and also the series could be divergent. So we are going to also look at that. So we have two examples to go. Why don't we get started?
All right, so we're going to start with part A, but just to recap a little bit, the series an is absolutely convergent if the absolute value version is convergent. Okay, if the series is convergent but the absolute value version is not, then we call an to be conditionally convergent. Okay. So then we're going to sort of like try to check if these series are conditionally or absolutely convergent. So let's start with part A. We have minus 1 to the n plus 1 divided by n square root of n. Okay, so let's start with that. First of all, this is an alternating series because we have the alternation going on here. And we have a designated test for that, which is the alternating series test. So why don't we apply the alternating series test for this problem? So let me just isolate the alternating part, which essentially means that we have n to the power of 3/2. We have two conditions to show. One is that limit of an is 0, okay, which is the case because top is a constant, bottom is approaching infinity. There we go, this is 0. And second, we want to have an to be decreasing, so there are alternate ways to show that, but I'm going to use the one given in the description of the alternating series test. An plus 1 is less than or equal to an. Here we go. 1 over n plus 1, radical n plus 1. Is it less than 1 over n radical n? Well, this is obviously true because n plus 1 and radical n plus 1 are certainly bigger than, greater than n and radical n. So here the bottom is going to be bigger on the left. So then you're dividing by a bigger number. So obviously this condition has to hold true. Okay. So what that means is two conditions are satisfied, and by the alternating series test, this is a convergent series. So we want to sort of like investigate further. Is it absolutely convergent or conditionally convergent? Okay, so I'm going to go ahead and look at look at the absolute value of the whole n term here. Okay? So I have the original alternating series and the absolute value of the whole thing here. Well, first of all, when I take the absolute value, I don't have the sign alternating anymore because this is sort of like absorbed in the absolute value. So this is essentially the same as the series 1 over n radical n, which is equal to 1 over n to the 3 halves. Okay? So it's interesting because when you take the absolute value of the n term for this series, right, then what you get is a known series. In fact, it's a p series. So p series with p equals 3 halves, which is strictly greater than 1. And we have the p series test ruling that this is a convergent series. So the absolute value version of the original series is convergent. Okay, so I can go ahead. I know that this is convergent already because I used the alternating series test to prove that. But I can go one step further. I can conclude that this is absolutely convergent. Okay. All right, for part B, I'm going to look at the same thing. But before I jump into that, I need to simplify the top. So what is the meaning of sine of 2n plus, so 2n minus 1 pi over 2? So you're talking about the odd multiples of pi over 2. So what do they look like? Well, it looks like sine pi over 2, sine 3 pi over 2, sine 5 pi over 2. Let me just write one more term, 7 pi over 2, on and on and on, right? Well, sine pi over 2, if you use your TI-84, it's 1. Sine 3 pi over 2, on the other hand, it's minus 1. Okay, check your calculator. 1 and minus 1. So there's some alternation going on here. Interestingly, there's a hidden alternation going on for this term here. So this makes this series an alternating series. But how am I going to represent that in the form of alternating series? Well, since this function takes the value, or this number takes the value either 1 or minus 1, so I'm going to convert this into the form, let's say minus 1 to the n or n plus 1. I have to think about it. Because the very first term is the one corresponding to n equals 1. So it's plus 1. So if I choose minus 1 to the n, minus 1 to the 1 is going to be minus 1. That's not going to spit out 1, so it should be n plus 1. So the exponent for the first term, which is n equals 1, should be positive 1. Here we go. So I have to make the top n plus 1 so that the next term is going to be minus, plus, and on and on and on. Okay? So it's interestingly, this and this series are exactly the same. But this is a known series because it's an alternating series. And we have a test to determine the convergency of that, which is the alternating series test. Okay? Well, I'm going to use the alternating series test, but eventually, since the goal is to show if this series is absolutely or conditionally convergent, I'm going to write down the absolute value version of that right away here. Remember, when you take the absolute value, there is no alternation anymore. So this term, in other words, is gone. It's 1 because it's either 1 or minus 1, but when I take the absolute value, it's going to be always 1. So this series, in other words, will look like 1 over n only. I'll talk about that, okay, for the convergence because it's a known series. For this one, alternating series test is applicable for a n equals 1 over n, which is the non-alternating part of the for the general term, right? So number 1, in the alternating series test, the limit of a n should be 0. Well, it's obvious, right? And an plus 1 should be less than or equal to an. Here we go. 1 over n plus 1 is always less than or equal to an, which is also obvious, right? You're dividing by a bigger denominator here. Boom. So two conditions are provided to us and two conditions are met. So I can go ahead and I can say like this is finite. So it's convergent. Okay, good. How about this series here? It's 1 over n, just 1 over n. And this is a P series. And P series are divergent when P is greater, P is less than or equal to 1. And in this case, P equals 1 because this comes with power 1, right? P equals 1. So for P equals 1, P series is divergent. Unfortunately, this is plus infinity. So this is divergent. The absolute value version is divergent, whereas the original version is convergent. So that makes this series not only convergent, but conditionally convergent following the definition of conditional convergence here. So the original series is convergent, but not the absolute value version. Okay, that's divergent. So to sum up, in the first part of the question, we had an absolutely convergent series because both the series and the absolute value version were convergent. And for this one, the first thing was like to observe that this is an alternating series because sine 2n minus 1 pi over 2 takes the values like -1 and 1. So that makes it an alternating series. Once we get to that, we checked both itself and the absolute value version. And absolute value version turned out to be divergent. And in fact, as a side note here, this series is called harmonic series. It's also another well-known series. Harmonic series is divergent. Okay, so the absolute value is divergent, and the series itself is convergent. Here we go. That makes it a conditionally convergent series. All right. I think that's all it is. We went through two good examples to practice a conditionally and absolutely convergent series. If you have any questions or comments, please send those to my way. And that is the end of the video. Thanks for watching. I'll see you in another video. Bye.